Hello everybody. Today we talk about very basic but very important aspect of the LSI digital chip design, and it's a digital, but it's a lot of knowledge come from the analog side, and it's a most of people don't know unless you have really in-depth study of the LSI logic design. For example, you have NAND, and this logic is very simple, and you think logically there's no issue, but there are a lot of physical aspect of it. And for example, if this NAND drive is going to go to one of other gate, has a long distance connection, and another long distance, and another long distance, and another long distance. So what's happened is how many you can drive. Logically, there's no issue, but electronics tells you this has a big issue because the NAND gate made minimum like 7 nanometer technology. It's a very tiny transistor driving from corner of chip to other corner of chip. It's long wires, has capacitor, a lot of capacitor, and now this is going to be so-called Fanout problem. So the CMOS device is driving basically capacitor. Other gate has all gate is capacitor, and the wire has a capacitor. So when you exceed the fan out, you know the exponential function, and we went through in the analog circuit. It's going to be, usually it's go up to high like that. So it may go up to high like that, okay, and usually go low like that, exponent, but it may go like that. So that means, say this is half point, this is the half point, you have this much extra delay, and usually this gate operate at 1 nanosecond. You may have 10 nanosecond, okay. So when fan out is the fan out rule exceed, it's each logic element in the library has a standard fan out. For example, NAND gate, you can drive up to 4 other gates, and delay time is specified. But 4 other gate, when 4 other gate is far away, the wire capacitor comes in, then this delay time, gate delay time, is not guaranteed anymore, right? And this kind of rule, it said average 4 gate with average wire stuff, right? And then we kind of guarantee TG, the gate delay time. But it's if you have a million transistor on the die, there's no guarantee. Some wire may go from here all the way to here, and some device goes all the way here, so and so. Okay, so the library has no function buffer usually, and provide a large fan out, or it can drive 10 gates, and this delay is such and such. The average 10 gate, but if 10 gates is all far away, then again it's gonna be issue. Okay, logically we don't need this. This is what? It's just buffer. There's no logical function, but we still need it, depend on what kind of logic design you do. And when you write nice program code, said, okay, we need a function, this kind of logic, okay, and translate it into the gates library, okay, nicely done. But depend on software, how well the software, some software confirm that this gate can drive up to 4, and if not, if this translated logic is driving more than 4, then it's insert buffer. Depend on software, okay? Then it take care of fan out issue. Okay, the problem is when you have that kind of problem, when you move from 28 nanometer process to 7 nanometer process, and you have a logic library. Now, this buffer, how do you increase the fan out? Scaling transistor. So it's use more current, but power drive the output, right? So when you move from here to here, small transistor, obviously gate current is much smaller, and we say, yeah, we used to drive 4 fan out, and when you shrink transistor, this other transistor is small too, so we still go for fan out. This scaling is not that correct, because first of all, wire lengths same, pretty much same for both process, okay? And this is a exponential function you have, right? It's switch like that or switch like that. This much delay is different, and you can linearly just say, oh, everything scaled correctly, so still fan out of 4. It's not. This require a lot of chip testing for new process. And who does that? Usually one chip company making their own chip, internally they have engineer who does qualify for those library parameters. They make a lot of test chip and find out actually what kind of fan out and delay time it can be done. But right now in the industry is kind of chip company the logic, mostly logic design, and manufacturer like a TMC, and they don't do this kind of evaluation. It's they just scale it, right? And tell chip company, give me your ESD tape to make a chip. So the chip company has to do it, but the Qualcomm, those companies don't have the engineer who does this kind of evaluation. So they just say, okay, fine, we scale design and end up like this. We added more chunk of logic because the scaling allow me to add more logic, that's it, and give a new tape, and manufacturer just process it, assuming that okay, it can have same fan out and stuff. Okay, then it doesn't work. So logically it's exactly same, but scaling is this a physical issue. Okay, so the physical problem has to be resolved, not a logical issue. Okay, so suddenly the yield drop, right? And usually yield is you have one wafer and how many good chip you get, that is yield, right? And now say from 8-inch wafers I can get about 300 good LSI chip. You scale from 28 nanometer to 7 nanometer, then it's dropped to only 3 good chip. Okay, the yield is usually the cause of the bad yield is the silicon crystal defect, and the processing diffusion has a variability. Some area the diffusion didn't go as we expected, and of course dust, and those crystal defect and the dust, those issues are pretty much handled for both cases, right? So it's still 300 yield dropped to only 3 good chip. This is gonna be very expensive chip. It's not commercially viable. Okay, it's not because of this. This is a circuit, analog circuit issue. Wait a minute, this is a digital design. Digital, why analog coming? Well, if digital, but the gate is an amplifier, okay? And when you switch from low to high, the current flow like this. And this characteristic, you can increase the amount of current by scaling this transistor up. And this current, total amount of current, and this, say if it is time, total Q, that Q is charged, is used to charge up all the capacitor here, capacitive load, right? So this is obviously analog issue. And also, when you switch in the middle around here, this gate is amplifier. And you know what happened to the amplifier? When you have gates cascaded and if signal is kind of not high, not low, this is the gain is at the highest for this digital circuit amplifier. And if it's cascaded, if signals stay long between high and low, this gonna be very big total amplification. And what happened if this wire happened to be close to this, feedback happen. So this feedback can cause oscillation, right? So within the digital circuit, have you ever heard of oscillation happening? Well, this is a probability issue and the physical issue, physical design issue. It's logically zero issue, okay? Logically zero issue, but now you're bringing a lot of physical problem by scaling from 28 nanometer to 7 nanometer. So the yield suddenly dropped. You heard that Apple's try to make a 4 nanometer chip and a 3 nanometer chip, but yield is terrible. TSMC, they said we cannot get the yield. Of course, Apple design logic. TSMC makes chip. But chip technology, there is something between here. Physical design issue. Somebody need to take care of it. The Apple has it. TSMC has it. Well, that's a really question, right? I know when the long time ago, the chip design is done by chip manufacturers, and they have a set of design engineers who does this kind of qualification. When you scale it, what happened? All the physical issue is bugged out. But who is going to spend the money and time and the cost to bug out this? Chip manufacturer or chip designer? I don't think chip designer can do this. This has to be done on the chip manufacturer. But chip manufacturer is willing to spend that much money to bug out all the bug, physical bug. This is a real world problem. Okay, so the scaling is not that easy. It's not just changing transistor size. Every physical parameter changes around. Okay. Now there is a chip testing issue. When you created a chip, this chip function is identical to the logic design. How do you verify this? When it comes to the complex chip like CPU, this is impossible. Okay, the best you can do is say, yeah, I think 80% identical kind of deal. Okay, what you do is you have input and output. The problem is inside has registers and memory. It's impossible to test all the cases, and you spend a lot of time testing. No matter how much time is testing, there is a case that never happened in the internal logic. That means there is a case that you never tested. So it's almost impossible to say 100% this actual chip function is same as logic design. Now within this 80%, if there is a difference you find, aha, this chip is a defect, something wrong. It doesn't do exactly as logic design say. Well, actually, it's not true. Sometimes, example, throw clock, then it's match up. The test pattern, you generate a test pattern, right? And you run it on the probe. You have a chip, and you put the probe and the test machine run this test pattern, and you decide whether it's pass or fail. And sometimes test is throw clock, it's pass, good, and run on the workbench, making a motherboard and put chip, fail. So clock is too fast. You slow down the clock, it works. So it's not just a logic test. There is an issue of timing. And when the clock speed doesn't meet, what do? Think about it. What can you do if the chip you made is supposed to run 1 gigahertz, but it's passed the test only 200 megahertz? And this is the case like some company use FPGA to make a microcontroller, the CPU, and they don't know what the actual final clock speed they can run. And they think, oh, this FPGA 100 megahertz, it's passed the test. You put in a board and run 1 month, fail. Because there's some case, it's not test pattern came up and it's fail. So when the FPGA, those chips, very difficult to predict what the clock speed will be at the final. It EDS kind of tell you what's going to be, but when you run after programming, cutting a fuse and stuff, a lot of unused metal hanging around, and the gate speed, delay time is not guaranteed, and it's become very slow. FPGA tend to be very slow clock, and even that, what we like to know is it's guaranteed it's run at 100 megahertz. Good, this microcontroller, we can use it for some controlling, but there's no guarantee because test pattern cannot test 100%. It's only actually this screening, this is called screening. 80% this test pattern is just too huge, reduced down to say 20%. And simplified test pattern is used to screen the chip from warehouse, and you think it's run, you hope it's run, but you never know when it's fail, when the clock speed increase. And that's why some people buy Intel CPU, put in the motherboard, and increase the speed, clock speed, and still run, window run, great. Okay, it's okay to use, then sometimes say 1 month you get the green screen. And some chip, no problem, 1 year, keep running. Okay, when Intel sell the CPU, they tested at a certain clock speed, and they cannot test so many different clock speeds. So they say, okay, this one seemed to be okay with a 20% test pattern, then they sell it. And there is a distribution. When you sell it, the chip run at the 20% most of the time. here, and some of them run even higher clock. Okay, so this is a really serious issue that we cannot really address well. Then what do you do if you make a CPU chip for the cell phone? The cell phone has a CPU chip. Great, we got the 4 nanometer latest process CPU running, right? Well, actually there's not much harm. If it's a fail, just restart it, right? But you can't do that for like a satellite, and you cannot do that for military. There are certain applications you have to be very conservative, and you cannot say, hey, new process, it's great working. That's why those applications that require the reliability is very conservative. 28 nanometer is the maximum you can go. Even 120, 250 micro nanometer, right? Yeah, chip. This already used many years, and it's kind of guaranteed it works. Those are the use. This never use this kind of things in critical application. Cell phone is fine. If something go wrong, just restart, right? In tablet too. So this become very practical decisions about the chip. The testing issue is not resolved. There's no good way to test it. Now, last one I want to mention is the bus, internal bus. Okay, internal bus on the PC board, you use a tri-state bus. What tri-state is? Everybody disconnect high impedance state. Only one using bus drive the bus, right? And this is not going to be used on chip. The reason why this is used is the pin count. You can't afford to have input data and output data separate pin on these chips. So the data bus is bidirectional. This is the PC board. On chip design, you always separate in and out. Okay. The tri-state, don't use it because it's caused a lot of problem on chip. Because tri-state, if you make a bus like that on chip, and typically the bus get a lot of capacitor, and it's the rise time issue. We want nice ramping up high and nice going down low, and it's become like this. This is definitely an issue internally. If you have a lot of capacitive load, actually when you get the capacitive load, the typical one is address. You have 32-bit or 64-bit register, and you have to select register by address line. This is gonna be very heavy capacitive load, and the signal become like this. This rise time, fall time. you can't have this kind of very prolonged slow signal, because it's caused a lot of problem. Here the amplifier gain is highest, and all kind of bad things happen. It's almost unpredictable what's happened, depending on what kind of wire is crossing around this amplifier. Okay, so you use high drive buffer on chip to select, or you have to select only 8-bit, 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 and use a 4 buffer. Then you have a variability of delay time. This buffer and this buffer is slightly different, and the difference, you have the worst case difference you have to calculate into the critical path. And this kind of design consideration, you never do it in the FPGA. The FPGA pretty much forget about timing. It's hope the chip come out to be usable. It's like, okay, at least this CPU seems to run at 80 megahertz clock. Great, I think we can use it. You know, so it's a little bit different philosophy. And this kind of design is a part of chip designer. It's not just logic. Okay, so there are still a lot of physical issues to deal with in the digital design. Okay, that's it for today. If you think this lecture was good, please subscribe.